Welcome to this session, which is going to be a Dissertation Award talks. It's my pleasure to be a host of it. Thank you so much. My name is Irina Skripnik. I am a director of data science, advanced analytical solutions at a pharmaceutical company, Eversana, and also co-chair of applied data science track KDD 2021. So today we have two winners, two presenters of best works, first place and runner-up. And shortly we are going to listen to their presentation. I would like just to say that I'm very happy for you guys and congratulate you on this great achievement and this great award. PhD thesis or any thesis is always a great journey, and we all have sometimes mixed feelings about it and great experiences, and it's definitely worth to be shared. Even for those who defended it, we all remember ours and we get inspired. So I guess we would like to hear all about it today. As soon as you're gonna share your technical details as well as your personal journey through it. And it's a great feeling when you had that achievement. Sometimes, you know how they say that basically your PhD work is literally a path to a scientific career or a life when you have got to do a real research. And, we don't think like that when we do our PhDs. We want to get some achievement basically right there. So this thesis is your actual contribution and your work. And something that in this particular case, it's a high reward, it's a great reward, and your work is recognized, on which I congratulate you on completion of this. So our first presenter today is going to be Aditya Grover, and his dissertation is about learning to represent and reason under limited supervision. So Aditya, I give it to you. Please also tell us about yourself and begin your presentation.
Yeah, so I want to start this talk by saying I'm incredibly honored and humbled to receive the ACM KDD Doctoral Dissertation Award. And I did my PhD at Stanford University last year. I graduated last year, and I'm incredibly also delighted to share some of those research works with all of you today. So my thesis was titled Learning to Represent and Reason Under Limited Supervision. And the motivation for this thesis was really that in recent years, there has been a massive growth in the scale of data and computation in a variety of disciplines, such as the earth sciences, materials, engineering, and biology. And the scale provides us with an unprecedented opportunity to extract useful knowledge to make inferences and decisions. However, it so turns out that in many cases, the raw data that we collect via sensors is limited by the available supervision signals, such as labels for prediction. And obtaining such explicit supervision can be an expensive process due to costs such as time, money, and safety. So the key theme of my dissertation and this talk is how can we mitigate the supervision cost for machine learning systems. So in the last decade, the most successful methodology for training machine learning models with less supervision followed a two-step recipe. Pre-train very deep neural networks on a large labeled data set, followed by fine-tuning on your target data set, which is relatively small and domain-specific. For example, pre-training on ImageNet works extremely well for standard computer vision use cases. This pipeline, however, is still reliant on a tiny fraction of all the captured image data that exists in this world, in our phone cameras, on the web. And moreover, a bigger problem with relying on ImageNet pre-training is that we do not have such data sets for domains such as climates, drugs, materials, and energy. So instead, what I want to argue that the success recipe for the next decade and beyond will drop the supervised pre-training requirement and work entirely with unlabeled data. Not only does this pipeline extend readily to supervision-hungry domains in science and engineering, it also enables us to truly utilize internet-scale, ever-expanding data sources. Now, as attractive as this proposal sounds, the key question is that what is even the learning objective for unsupervised learning? Now, unsupervised learning has been a long-standing goal in AI. And while traditional perspectives to this problem have focused on clustering and dimensionality reduction, the key breakthroughs in the last few years have primarily stemmed from combining deep neural networks with two kinds of learning objectives: contrastive learning and generative modeling. My PhD thesis has looked at both contrastive learning and generative modeling. In fact, the very first paper I published in my PhD 5 years ago was at this very conference, proposing one of the first contrastive learning objectives for representation learning on graphs. Today, in the interest of time, I'm going to focus on some other works during my PhD that relate with generative modeling. In particular, the first and predominant part of my talk will touch upon some key foundational questions in generative models, such as the issues of bias and generalization. Towards the end, I will showcase how these ideas can be combined with decision-making for climate science application relating to optimizing electric battery charging. So let's get started. As you might have seen, some of the most impressive demonstrations of AI in the public sphere in the last 5 years have focused on generating data. It started off with generating high-resolution imagery from scratch, to very recent developments in translating natural language instructions to code. And alongside language and vision, these models have now been successful at simulating geographical phenomena such as earthquakes and floods, synthesizing drugs, catalysts, and materials, among many other fascinating use cases. So the key technical framework behind generative models can be formalized as this very simple problem, where we observe samples from an unknown distribution P data. For example, we might observe an image data set of monuments, and the goal will be to approximate this distribution as closely as possible. In order to do so, we pick a model family M and optimize for the member of this family Pgen that minimizes some notion of discrepancy with respect to the data distribution. The key challenge in high dimensions is the curse of dimensionality. Our data distribution can contain many, many modes, and our training samples cover only a very small region of the true support of this distribution. So in today's talk, I'll present vignettes of my research that address this curse of dimensionality for generative modeling. First, I'll talk about generalization, and where we look at a popular class of learning objectives which are by default not designed to be robust to training site memorization. And thereafter, once we assess generalization on these models, we'll also look at how we can exploit additional sources of unlabeled data for sample efficient learning without introducing prohibitive bias due to the data set itself. Okay, so let's get started with the discussion on generalization. So a very popular class of generative models in use today are generative adversarial networks, or GANs, where the generative model G is a latent variable model that takes in a source of stochasticity Z that's sampled from some analytical prior, such as the isotropic Gaussian, and it is passed via a differentiable mapping G to obtain a sample X. There's another network, a discriminator critic F, which distinguishes between real samples and generated samples and competes with the generator network, which is in turn trying to best fool the critic in a minimax formulation. Now, GANs work great and power many of the technological successes I showed you earlier in this talk. But for a long while, they were very subject of criticism that these models are simply memorizing the training set, which would trivially lead to excellent sample quality. Some prior attempts have tried to resolve this issue by making discrete approximations to the support of the distribution, but that's not reflective of real-world use cases of these models. The key metric of generalization is the likelihood of the model. Likelihood is basically the probability that this model assigns to a data point. If a model is indeed overfitting or memorizing the training set, it will assign low likelihoods to an unseen held out set. And then naturally, the question that we should be focusing on is, for a GAN, what is the likelihood it assigns to the held out set? Turns out it is mathematically not well defined for an arbitrary class of differentiable mappings M. But what I'm going to show next is that if we restrict the model class M, then we can ensure that the likelihood is indeed well defined and tractable. So our construction is based on the observation that if we let the latent dimensionality K equal the data dimensionality N, and we define M to be the class of invertible functions, then the likelihood of a GAN is indeed well defined and tractable. And this fact directly follows from the change of variables formula, which states that let H be the inverse mapping of G. So it takes you back to Z given an X. Then the probability density at X equals the prior density at the inverse of X times the change in volume, which is mathematically nothing but the absolute value of the determinant of the Jacobian of H at X. Now, I'll not be covering the various ways in which we can make deep neural network mappings G invertible. There's a good survey in case you're interested. But what's important to note is that by restricting the model class to be invertible, we now have a handle on the exact likelihoods assigned by the model and can evaluate generalization of GANs beyond the training set. Okay, so next we did an empirical analysis of GANs with this invertibility constraint on two different objectives for CFAR10. First, we trained them via maximum likelihood estimation, and we have no minimax training here. So we observed an expected trend where both the training and validation curves in red and blue are closely following each other and decreasing over the course of training as one would expect. The likelihoods are increasing in this process. The generated samples also gradually improve from random noise to somewhat more interpretable structure. Next, we train invertible GANs with the more commonly used adversarial minimax objective. So the same model, but a different learning objective. And here we find a couple of interesting trends. First, we find evidence that GANs do not overfit on the training set. The training and validation curves closely follow each other throughout the course of training. However, these likelihoods are getting worse during the course of training, and even more so by several orders of magnitude, even when the sample quality is improving. So what's really happening? So we dig further to find evidence that adversarial training actually severely degrades the conditioning of the Jacobian of the generator mapping. And this is a natural suggestion of how we can regularize the model. So we combine both these objectives of adversarial training and maximum likelihood, and the details are there in our paper in case you're interested, and this greatly stabilized our training. So to summarize what I just described so far is that this work was one of the first to show that GANs can have tractable likelihoods and are not memorizing the training set. And in doing so, we also got further understanding of how to stabilize their training via controlling their conditioning. So this was this discussion I wanted to have about generalization of these models. And next, I want to go to this question of dataset bias in these models. So to motivate this part of the talk, let's look at some celebrity faces drawn from a state-of-the-art generative model. Now, the sample quality is great, but there's a concerning pattern when you try to classify these samples by gender. So the orange line separates out the two classes. And as you can see, there's a huge disparity in the two genders. Now, on one hand, this should not be surprising, given that the majority of the face data sets propagate certain kinds of stereotypes with respect to gender. On the other hand, it's concerning because unsupervised learning can learn from all these different available data sources and amplify the stereotypes because its task is to generate more of this kind of data. So formally, what we're really saying is that in this nice picture we had, we are in this scenario where we have a small data sample. So to enrich our data sample, we start collecting auxiliary data sets. These data distributions are different from the ones we care about, but they're close. And the question we're interested in is how can we leverage these auxiliary data sources, P1 and P2, augment them with P data to better learn the generative model for P data. Now, you can take an example. So for example, here I'm showing on the left a very small data set of 4 images, which is biased, whereas here's a reference data set, which is not biased with respect to the number of examples of each gender. Now, if we want to combine these data sets, there are some simple solutions, but they have their obvious problems. For example, we could get labels for the biased data set, but this would be time consuming. It might also invade on privacy. We could completely throw the biased data set, but this is not sample efficient. We could mix these 2 data sets without worry, but then the worry would come later when the generative model propagates the same biases in under and over-representing certain genders. So really what we want is that learning of a generative model to be label-free, sample efficient, and mitigate the bias with respect to the data distribution. And none of these trivial solutions really get the best of all worlds. So our solution to this problem was based on this observation that really a learning objective of a generative model can be written as an expectation. And it's an expectation with respect to P data, but we now have additional data from a bias source. So the expectation has to be written with respect to the bias data source, but to match it with the left-hand side, we need to do a weighting correction. And this weighting correction comes from this density ratio, which is the ratio of the data density to the model density. So the next piece of the puzzle to fix is where does this weight come from? And it so turns out we had derived in the paper a very nice estimator, which is based on simply binary classification. So again, I won't go into the details, but the overall algorithm looks very simple. We train a classifier to distinguish between these 2 data sets. That gives you a notion of importance weights. And these weights can be then used to upweight or downweight points such that this entire data set can be then used to train your model. This entire procedure did not require at any point labels of what's male, what's female. We need no gender labels here. It's sample efficient because it's using both the data sources. And as I'll show next, it also reduces the bias in learning compared to baselines. So to the same experiment as I had before, we have a biased data source that's propagating certain gender stereotypes. And then we have a reference data set that's balanced. If we try to do the density ratio estimation here, we indeed find that our estimator downweights the overrepresented group in this example, and it upweights the underrepresented group, which is consistent with what we want here. And then completing the whole algorithm, if we use these importance weights to then learn a generative model, we indeed find that there is a much better balance of the 2 genders, as you can see, based on this orange line that separates one gender from the other. And the sample quality also improves. Of course, the sample quality is being evaluated with reference to a fair balanced data set. So there's also an improvement in sample quality while we see this balance visibly much better than before. Okay, so this was what I wanted to talk about in terms of bias and generalization generative models. So in the remaining time I have, I want to briefly discuss how these ideas can be now used for applications in the real world that are addressing and mitigating the adverse effects of climate change. So in particular, I want to talk about electric batteries. So electric batteries are one of our key instruments in converting to a green energy economy. They can reduce our carbon emissions significantly. They can also provide clean energy for millions of people while creating safe and sustainable jobs. But there's a problem when we go to buy an electric car. We want our car to charge as fast as a gas-powered car. But if we do fast charging, it causes the battery to degrade, which is a significant cost concern for us. So the question we were really asking in this work is, can we optimize for ways to fast charge a battery while minimizing degradation? So in this multi-year project in my PhD, I collaborated with material scientists and chemical engineers at Stanford and MIT. And the challenges here were multifold. Not only is the search space very big, a single experiment means charging your battery on and off until it dies, which could take months to finish. And I didn't have so much time in my PhD, so I really had to do lots and lots of experiment while not making every experiment take months to finish. So our proposed approach was to learn a generative model for these experimental outcomes using offline data from related chemistries. And the advantage of this was that we can now integrate the learned model to terminate the suboptimal experiments. So if an experiment from a charging protocol is not working well, we just cut it short and we move on to the next experiment. Now, again, in the interest of time, I'll skip over the details, but the highlights was that we showed in our Nature paper last year that our pipeline was able to achieve a 5x reduction in testing time compared to a baseline approach, which would not cut experiments sooner. And more interestingly, we were able to discover charging protocols that outperformed the prior art in this field. So as a summary, generative models, contrastive learning, and their hybrids are at the forefront of the unsupervised revolution. And I'm very much looking forward to it. While on one hand, as I showed, we need a cautious outlook in understanding this branch of machine learning, both in terms of the algorithms as well as its adverse social impacts. On the other hand, I'm also very optimistic about the fascinating progress we have made as a research community during the course of my PhD and the thrilling possibilities ahead in using them for accelerating science and technology. I believe this dose of healthy, cautious optimism is necessary. As recent events indicate, the pandemic was a missed opportunity for AI and a necessary mirror into the shortcomings of our field. There are potentially bigger disasters looming for our future generations due to climate change. And to mitigate these challenges, I believe we need to move our focus to more open-ended evaluation of our models outside the fixed train validation test regimes, but also raising the bar for modeling to critically include aspects such as uncertainty quantification, causal reasoning, and multi-agent decision-making. Finally, I realize that this challenge is far from being solely a technological one. And as technologists, if we want to contribute to it, we also have to make an effort to build a community of AI researchers that works alongside other stakeholders to build successful solutions. I would like to conclude by saying that I'm incredibly thankful for this award and indebted to my PhD advisor, Stefano Erman at Stanford, and family, friends, mentors, and collaborators from India and US for their immense hard work and support in making this award and the talk research a reality. Thank you.
Thank you very much, Aditya, for the interesting presentation. And now I would like to request the audience. Are there any questions? Really, you can just unmute yourself and start asking the question.
Hi, I have a question. So I'm Claudia Plant from University of Vienna. And you talked about the classical branches of the unsupervised learning, which are clustering and dimensionality reduction. How would you say does your work connect to these classical branches? How can they be maybe used or integrated to improve your methods, or do you see any kind of connections?
Thanks, Claudia. That's a great question. How do classic perspectives on unsupervised learning, whether it's clustering or dimensionality reduction, interface with these modern methods, some of which I presented? And I think one of the great connections that arises between these methods is that many of these approaches, for example, autoencoders, can be seen as a nonlinear generalization of classic methods like PCM, but under certain assumptions. So the first aspect is that these deep methods are making these mappings for which are used for discovering patterns in our data in an unsupervised manner, nonlinear. And that enables us to find patterns within very high dimensional data, which might have not been possible with classic techniques. And where it benefits is really that the neural network might be the one that's enabling this nonlinearity, but the final objective function that we care about could be stemming from these classical approaches. For example, PCA cares about finding a low dimensional subspace which maximizes the variance in the data, an objective which we can also think about using for deep learning based methods. Similarly, there is work in clustering objectives, differentiable versions of clustering objectives, which are being used to train a lot of these unsupervised deep learning systems. So really, I think there are synergies in the fact that a lot of the theoretical underpinnings behind classic methods can be extended to modern deep learning methods designed for unsupervised learning.
Thank you very much.
Thank you for your question, Claudia. Any other questions? Don't be shy. It's a very interesting topic of research. Okay, I hope there will be like more questions offline. In that case, I would like to present our next speaker. Shweta Jain from University of California, Santa Cruz is going to present to us her work on counting clicks in real-world graphs. Welcome, Shweta.
Thank you. Hi, everyone. Thank you all for being here for my talk. I am very honored to receive the SIGKDD Best Dissertation Award runner-up. This work was done at UC Santa Cruz. I graduated last year, and my work is about counting cliques in real-world graphs. A big thank you to the SIGKDD and to the award committee. So graphs are everywhere, right? We have social networks, protein interaction networks, citation networks, routing networks, epidemic spread networks. Oftentimes these graphs, they run into millions of nodes and billions of edges. So for example, I have these 4 real-world graphs here. And as we can see, the number of vertices and edges in these graphs easily run into millions, if not more. So given such large graphs, a natural question is, how can we say something meaningful about these graphs? How do we make sense of such graphs? How can we say something? How can we summarize them? How can we characterize them? How can we compare 2 graphs? One way this is done is by looking at counts of certain patterns in them. So patterns like cycles, triangles, cliques, and so on. And the pattern that we'll be looking at today is the K-clique. So K-clique, as we all know, is just a set of K vertices all connected to each other. So we can have a 3-clique, which is a triangle, a 4-clique, 5-clique, and so on. And the reason cliques are important is that they often have some semantic meaning in the context of the phenomena that the graph represents. So for example, in the case of a social network, a clique of size 5 could point to a set of 5 pins. And indeed, one of the salient features of real-world graphs is that we observe that there are many more triangles in these graphs than what we would expect in a random graph of the same size. So these counts, they can actually tell us something about the process that generated that graph. So they've been used in dense subgraph discovery, in community detection, in graph visualization, in graph modeling. So for example, if you're trying to model some real-world graph, you may want your model to reflect the clique counts that are observed in that real-world graph that you're trying to model. And all of these papers that I've listed here have used clique counts in some or the other form. So when we talk of cliques, we can talk about them in multiple ways. We can talk about maximum clique, which is the clique of the largest size. We can talk about maximal cliques, which are cliques that cannot be increased further, meaning that there's no other vertex in the graph that we can add to a maximal clique to get a bigger clique. And then we have K-cliques, which are just k vertices all connected. And this k clique could be sitting inside another maximal clique. So I have a toy graph here, and I've listed down some of the cliques in this toy graph. When we talk of clique counts, we can talk about them in two ways. We can talk about global k clique counts. So that's the count of k cliques in the entire graph. Or we can talk about local k clique counts. So that's the count of the number of k cliques that every vertex and every edge is a part of. And this kind of information is useful in applications where we may want to weigh the vertices and edges proportional to the number of cliques that they are involved in. So just to give an example, here we have a toy graph, and I've listed down all the cliques in which 1 is a part of that clique. So all of these are the local cliques of 1. So our problem definition is simply this. We're given a graph G, and we want to obtain all global and local k clique counts for all k. We'll set some terminology. So let n be the number of vertices, m be the number of edges. Let alpha be the degeneracy of a graph. This is the parameter that shows up in a lot of graph algorithms. We don't need to go into too much detail into what this is. Suffices to know that this is a measure of how dense the graph is. And for real world graphs, this is typically small. So even for the value of alpha can range anywhere between 0 to n minus 1, where n is the number of vertices. And even for million node graphs, real world graphs, typically alpha is in the range of hundreds. So a lot of work had been done for counting 3 cliques, that's triangles. And some of that had been generalized for counting up to 5 cliques. But not much progress could be made beyond k equals 5. And the reason for that is combinatorial explosion. So here I have those 4 real world graphs again. And as we can see, the number of 7 and 10 cliques in these graphs easily runs into trillions, if not more. So enumerating these is not an option. And hence, subsequent methods have gone for either approximation or parallelism or a combination of the two. But there are limitations with that as well, and we'll talk about those as well. So in terms of what was known before this work, there exists a trivial algorithm, which given a k gives the number of k cliques in time n to the k plus 2. There exists a trivial algorithm, which for all k is able to count in time 2 to the n times n squared. The first major progress on this problem was made in 1985 by Chiba and Shizaki. They gave an algorithm which for a given k is able to count the number of k cliques in m times alpha to the k minus 2, where alpha is the degeneracy of the graph. And a lot of the subsequent work is actually based on this algorithm of Chiba and Shizaki. So we'll look at that algorithm as well. Following this was matrix multiplication. It was able to count the number of 3k cliques in time n to the omega k, where omega is the exponent for matrix multiplication. And then following this was our work pivotal last year, which is the work that I'm going to talk about today. It is able to count all k cliques in time n times 3 to the n over 3. So that's 1.44 to the n. And in terms of practice, so there have been a lot of practical algorithms defined using different terms, optimized for different things. But most of these are approximation algorithms, they're sequential algorithms, and they give global counts. The problem with these is that they typically only work for up to k equals 5. So of course, this depends on the graph on the graph structure, but for the graphs that we are dealing with, which are real world graphs with million node vertices, these typically work up to 5. Beyond k equals 5, the first algorithm that was able to count was this algorithm by Finocchi et al. It was a distributed algorithm, so they used MapReduce to do this. It was an exact algorithm. It gave global counts, and it was able to count up to k equals 8. Following this was our work, Chu and Shadow, in 2017, which was an approximation algorithm, and it was able to count up to k equals 10. Following this was KC-list, which was again, so KC-list and the Finocchi et al. Algorithm are both variants of the Chiba and Shizaki algorithm. And it was an exact algorithm. It was a parallel algorithm, was able to count up to 13. Pivoter, our work proposed in 2020, is an exact algorithm. It's a sequential algorithm, and it is able to count for almost all k, for almost all the graphs that we tried for. And it gives global as well as local k clique counts. Around the same time was count cliques by folks at MIT. This also was a parallel algorithm, another generalization of Chiba and Shizaki's. So to summarize our result, we gave an exactly counting algorithm called Pivoter. In practice, it gave us a speed up of more than 1000x, even over other parallel algorithms. It gives global as well as local counts, and it works for all k for a large number of graphs in practice. And we showed that theoretically, in the worst case, it'll run in time n times 3 to the n03 for global counting, and for local counting, this gets multiplied by n and n squared. So in terms of the results, this is a plot showing the time required for Pivoter, which is our algorithm, versus the time required by KC-list. KC-list is a parallel algorithm. It was the only algorithm at that point that was even able to count beyond k equals 10. We parallelized it using 40 threads. And what we did was, for the four of the largest graphs that we had, which were shown on the x-axis, we looked at the max k in those graphs. So the max k was 61, 201, 67, and 51. And we fed this k to KC-list. And so KC-list basically takes a k and gives the count for that k click, for that k. On the y-axis, we have the time in seconds. And the red bar indicates the performance of KC-list, whereas the blue bars represent the performance of Pivoter. In 3 out of 4 cases, in minutes, we were able to give not just the k-click counts for all k, but we were also able to give the local k-click counts. And KC-list, on the other hand, had not terminated even after 3 days. So, okay, so before we dive into the algorithm, it would be useful to get some intuition for what cliques are and how they behave. Cliques are recursive structures. What that means is that a subset of a clique is also a clique. So that suggests that one way to discover all cliques in the graph would be to start with a small clique, look at its common neighbors. From the set of common neighbors, we add a vertex to the clique, so we get a bigger clique. And now we look at the common neighbors of this bigger clique, and so on. And if we do this process exhaustively, we'll discover every clique in the graph. Okay. So the algorithms that I mentioned, KC-list, count cliques, as well as Pivoter, are variants of Chibanish-Zeki, and it would be useful to look at what this algorithm does. So essentially, it's a recursive backtracking algorithm that visits every clique. So given a graph, it orders the vertices of the graph and orients the edges from lower vertices to higher vertices. So in this way, it converts the graph to a DAG. And now one can show that counting the number of k cliques in the given graph is actually equivalent to counting the number of k minus 1 cliques in the out neighborhood of each vertex. So what the algorithm now wants to do is that for every vertex, it is now going to look at the out neighborhood of that vertex. And now in these out neighborhoods, the algorithm wants to count the number of k minus 1 cliques. So notice that it's the same problem we started with, just on a smaller instance and for a smaller k. So what does the algorithm do? It recurses. So for every vertex in these out neighborhoods, the algorithm spawns a branch, calculates the new out neighborhoods, common out neighborhoods. And now in these out neighborhoods, the algorithm wants to count the number of k minus 2 cliques. And this process continues until there are no more cliques left, no more subgraphs left. So at the end, what we get is what we call as the recursive enumeration forest. Now this has certain properties. Firstly, so every clique is represented by a unique root to leaf path. And every root to leaf path represents a unique clique from the graph. So I've highlighted the clique 1, 5, 6, and 8, and that is represented by this path 1, 5, 6, and 8. The clique 1, 5, 6 is represented by the clique 1, 5, 6, and so on. So corollary of that is that all cliques of size 1 are at level 1, all cliques of size 2 are at level 2, and so on. Also notice that every blue vertex here is a recursive call that the algorithm makes. What that means is that the total number of recursive calls made by the algorithm is equal to the number of cliques in the graph. And given that we've had graphs with 10 to the 40 cliques in them, obtaining this enumeration forest for such graphs is infeasible. So the way other works have tried to address this is by using parallelism And by stopping the exploration of this enumeration forest at a particular k, and so that's the k up to which they're able to count. But we wanted to ask a more fundamental question, which is, can we count without enumerating? So as a first attempt, one might think of using maximal cliques. Maximal cliques are cliques that cannot be increased further. So in this graph, 1, 5, 6, and 8 is a maximal clique, 2, 3 is a maximal clique, 3, 4, 5 is a maximal clique, and so on. Efficient algorithms for finding maximal cliques have actually existed since a long time. And indeed, the technique, one of the techniques that we use in this, which is pivoting, was actually first discovered and used for counting maximal cliques. So why are these relevant? Given a maximal clique of size S, there are exactly S choose K cliques in it. So if I'm given a clique of size 5, I know that there are exactly 5 choose 3 cliques in this. So if I have an efficient way of counting all, of finding all maximal cliques, don't I have an, by using this formula, don't I then have an efficient way of getting the count of all cliques? So if the graph consists of disjoint maximal cliques, we would be good. But real world graphs, they often consist of maximal cliques that overlap in very complicated ways. And so what would happen is that this triangle that's in the center that I've highlighted, it's part of this maximal clique, it's a part of this maximal clique, and it's also a part of this maximal clique. So basically, if we are to use maximal cliques to count cliques, then what we would have to do is we would have to keep track of whether we have counted this clique earlier or not as part of some other maximal clique. Essentially, we would have to do inclusion exclusion, and that is expensive. So it is not clear, it is not obvious how to count by simply looking at maximal cliques. So we're back where we started. What do? So we use an idea called pivoting. The problem with enumeration was that there were too many recursive calls. We use pivoting to compress the forest, so which means that we want to make fewer recursive calls, but at the same time, we want to keep track of exactly how much we have compressed. So recall that in clique enumeration, we explored the out neighborhood of every vertex. What pivoting says is that there is a way of ordering the vertices such that some of the trees can be folded into the out neighborhood of a pivot vertex. And those trees that were folded in, they need not be explored. And I'll explain this through an example. So say we are given this toy graph. We pick a pivot. So in this case, let's say I pick the vertex 1. We order the vertices according to this ordering. So the non-neighbors of 1, followed by 1, followed by the neighbors of 1. So the graph, the ordering would look something like this. And now what enumeration would have done is that it would have looked at the out neighborhood of every vertex. But we noticed that the tree of 5 is actually contained in the out neighborhood of 1. The tree of 6 is contained in the out neighborhood of 1. The tree of 8 is contained in the out neighborhood of 1. And this is precisely because of the fact that all the vertices that are following 1 are all neighbors of 1. So which means that any clique that the enumeration algorithm would have discovered in the trees of 5, 6, and 8, it is also going to discover in the out neighborhood of 1. Which means that we don't need to count the cliques that are discovered by the enumeration algorithm in the trees of 5, 6, and 8. What we can do is only explore the cliques in the out neighborhood of 1 and count those twice. So if we find a 3 clique there, we counted once as a 3 clique and once as a 4 clique by adding 1 to it. So the vertex 1, we can treat that as a special vertex. We can treat that as a yes/no switch to the question, do we want to include this vertex or not? If we include that vertex in the clique, then we get a clique that the enumeration algorithm would have discovered from the tree of 1. If we answer no, then it represents a clique that the enumeration algorithm would have discovered from the trees of one of the neighbors of 1. And now notice that we are in this situation at every recursive call. So basically we can apply pivoting at every recursive call. And the resultant tree that we get is what we call as the succinct clique tree. So where the enumeration forest would have looked as what I've shown on the top, the SCT looks at as what I've shown at the bottom. It has far fewer nodes. And this was a small toy example I took, but one can imagine that in a bigger graph with bigger cliques, the compression would actually be quite significant. So for any path, this SCT, it has certain properties. For any path of the SCT, every unique set of yes/no decisions corresponds to a unique clique in the graph. So for example, on this path 4, 5, and 6, I have one green vertex and 2 red vertices. So with the green vertex, I don't have a choice. I have to take that vertex in the clique. But with the red vertices, I have a choice. So if I answer yes, yes, then the clique that I get is 4, 5, 6. If I answer yes, no, the clique is 4, 5, and so on. In other words, it has what we call as the unique clique encoding property, which is that every set of yes/no decisions on every path from the SCT corresponds to a unique clique from the graph. And every clique in the graph has exactly one path in the SCT and exactly one set of yes/no decisions on that path that corresponds to that clique. In other words, there is the bijection. So once the SCT is generated, we simply calculate the number of all combinations of yes/no decisions using formulas for every path. So for example, on this path of 7 vertices, it has 4 red vertices and 3 green vertices. Let's say if I want to count 5 cliques. So I don't have a choice with respect to the green vertices. So which means that out of 5, 3 vertices have already been chosen for me, but I need to choose 2 more vertices. And these can be picked from the red vertices in 4 choose 2 ways. And that's how many 5 cliques are supplied by this path. For the running time, so if you let n minus q be the number of non-neighbors and q be the number, n minus q be the number of neighbors and q be the number of non-neighbors plus the pivot, then we know that there are q recursive calls made. And if we choose the pivot to be the max degree vertex, which means its degree is n minus q, then the size of each subproblem that we create is actually at most n minus q. So in terms of running time, this translates to if Tn is the worst case running time for a problem of size n, then Tn is less than or equal to max overall q of q times t of n minus q plus O of n squared. This n squared work is required to build the graph at every recursive call. And one can show that the solution for this is actually 3 to the n over 3. This analysis is tight. We can show that the size of the SCT has to be at least the number of maximal cliques in the graph, and there actually exist graphs with 3 to the n over 3 maximal cliques. These are called Moon-Moser graphs. So our final theorem looks as follows. Pewter can obtain all global per vertex and per edge clique counts in time n alpha 3 to the alpha over 3. For the per vertex and per edge, it gets multiplied by alpha and alpha square. And all of this can be done in at most alpha square extra space over what is required to store the input and the output. And there are some interesting properties that were revealed by this. So we looked at the size of the SCT, which is proportional to the running time. So on the x-axis here, I have the number of edges. On the y-axis, we have the size of the SCT, the number of nodes in the SCT. Both are on log scale. And the line in between represents x equals y. Every blue dot here corresponds to a graph for which we looked at the size of the SCT of that graph. And it seems to be roughly proportional to the number of edges in the graph, which is a very surprising fact about real-world graphs. So there's actually some structure here, and understanding this structure better could lead to faster algorithms for other problems. In terms of time, so we have those 4 graphs, and we compared with Turan shadow and KC list. So Turan shadow is an approximation algorithm, KC list is a parallel algorithm. And in terms of seconds, so we basically ran Turan Shadow and KC list for k equals 13. And in much less time, Pivoter was able to count not just the number of 13 cliques, but the number of all k cliques in these graphs. So to conclude, we presented an algorithm for clique counting that is able to count all k cliques in graphs with millions of nodes and edges, and is orders of magnitude faster than even other parallel methods. We also improved the worst case running time of clique counting from 2 to the n to 3 n times 3 to the n over 3. There are some open questions that were revealed by this, which is why is the size of the SCT so small? That's a surprising fact. And whether pivoting and similar ideas can be used to get faster algorithms for other subgraph counting problems, like counting pi cliques or counting k-plexes and so on. Thank you.
Thank you so much. Any questions from the audience?
Hi, can I ask a question?
Sure.
I thank you first for your great work and presentation. I had a chance to take a look at the code for Pivoter, and I had a question. Is there a way to keep these SCTs or like print them? Because my understanding is because of being fast and like this recursive call, you don't print them, right? Is there a way to get the SCTs actually?
Sure, yeah. I mean, it's actually building the SCT, right? So it would just be a matter of printing out what structures it has at every recursive call. But yes, it's very easily doable.
Because my understanding was that because at each recursion, it removes that particular node from the memory. So I thought maybe it's not possible to print, like get that SCT.
No, it is possible. So we're not yeah, it is possible. We've actually done this in the past.
Oh, okay. Okay, thank you.
Any other questions?
Feel free to reach out to me offline and I'd be happy to help you print out the SCT.
Yeah, that would be great. Thank you.
Are you both actually having your work available offline for public or not?
Yes. The dissertation as well as the code is public. So yeah, feel free to use that. And if you have any questions, feel free to reach out.
That's good to know.
Yeah, likewise, my dissertation is public.
Okay, let's wait for another minute in case we have any more questions coming. So as we have a few more minutes before we close this session, I would like to ask you guys a little more relaxed, not technical questions. So what was your biggest challenge through your dissertation journey, and what you enjoy the most, what you discovered for yourself the most? So we start with you, Aditya, if you don't mind.
Yeah, that's a very, very good question. And I think
take a minute to think about it if you haven't.
yeah, I think it's surprisingly, I think for both questions, I would say the answer is similar for me, in the sense that I feel the uncertainty in research can get the most discomforting at times. I spent my second year working on a lot of failed projects, but failed at that time. And I realized in later years that actually none of them were really failures. They were just making me aware of what's the path to actually making things work. So I think that fact, the journey of research, because the uncertainty can get very discomforting, and it still does. It's not like it goes away. Even today, when things don't work, of course, it's like not the best of times, but then the prize is also bigger when you win, or when you see the result that you make things work, and then you realize that you're actually expanding human knowledge in ways that very few professions give you. So I think it's also very exciting in that moment.
Yeah, it's similar for me. I mean, there were definitely some lows, precisely because of this, that you don't know where your research is going. You don't know, like, there are no results you're seeing. And I guess I learned that, you know, if you keep powering through and you just stick with it, over time, something good will happen. At least that happened in my case. Maybe it's survival bias, but that's what I can say from my case. But there was that. I also learned to reach out for help. I mean, especially like the PhD is taxing on many levels. It's not just the work, it's also the fact that we are working in isolation. We are in, you know, in areas that are, we don't, like, we are struggling with things, and it's okay to struggle. Shouldn't be afraid to reach out. Other than that, I also discovered that, so I decided to get a PhD very late in life, but I was very, very happy that I did that, because at the end of it, I realized that I really, really absolutely love research, and I'm in the right place doing the right thing. So yeah, I mean, there were definitely, you know, hard moments, hard instances, but overall, I'd say it was a positive outcome.
Okay, thank you so much for sharing, and congratulations to you guys once again for completing this, for getting this award. I congratulate your supervisors as well for having such a great students. And I would like to wish all of the prospective PhD students, if you have, especially today in the audience, to have successful completion of this important work, of this journey. So thank you very much once again. And at this, we are closing today's session. Best of luck to you guys, and success in your career.